Okay, let's go ahead and take a look at some more fun KSP problems here. In this video lesson, what I'm going to talk about are precipitate formations, and this is going to be the opposite of what we were looking at with the other reactions. Previously, what we were looking at is taking a solid and adding it to the water to see if the solid will dissolve. In this case, what we're going to do is we're going to take two separate solutions. Okay, one will be the silver nitrate solution, and the other one is going to be a solution that has sodium sulfide in it. We're going to mix these two solutions together, and what's going to happen is that the silver ions are going to react with that sulfide ion to make our silver sulfide solid. At least that's the whole the goal. We want to know if that precipitate is going to occur. Will we get a solid to form when we mix these two solutions together? Okay, so when we talk about this in qualitatively, we just assume that because it was insoluble it will form. Well, now it's not always going to be the case. So how are we going to do this? Well, we need to keep in mind that when we are looking at solutions, we talked about this before, if I have a volume and a molarity, that's going to tell me the moles. Volume, molarity is going to tell me the moles. Okay? So what I'm looking for here is I'm looking to go back to the equation for solubility. Okay, so what I'm going to do is I'm going to start with the reaction going backwards. Even though we're going to try to form the solid, we're going to go back and use our equilibrium in this way. Why? Because our KSPs are always written in this format. Okay, so we're just going to treat this equation just like we normally do. Put a 2 in the front here, make my sulfide a -2. And what I'll do is I'm going to look at how this reaction plays out. Now, think of this as our initial conditions. Okay, we want to know if the reaction is going to shift right or if it's going to shift left or if it's already at equilibrium. Okay, if the reaction shifts to the right, we would say that the ions are going to stay in solution, meaning that we're not going to get a solid to form. If the reaction shifts left, then we're going to get a precipitate form. Okay, and if it's at equilibrium, then we're not going to have a precipitate form either because it's already going to be at that stage, and we don't really think of a solid being formed in a, when we're at equilibrium. Okay, so how are we going to do this? How do we know if a reaction shifts left or right? Well, if these are the conditions we're given, we're going to calculate Q for the initial conditions. Okay, for the conditions that they're giving us. Okay, so we're going to go ahead and calculate Q for silver ions, and it's going to be squared, and my sulfide ions to the first power. Okay, so there's my Ksp, if you will. Okay, so these are for the conditions that are given in the problem. Now, one thing you got to watch for is that you are taking a solution and you're mixing them together. Remember, we did this quite a while back, but we're adding these two solutions together, so we've got to make sure that we add the volumes. So therefore, our concentrations are going to change. So you have to plug in the new concentrations, and what you can do is use M1 V1 to do that. Right? We used this equation before because we're just diluting the solution down. So my M2 is going to be 200 milliliters times 1.3 times 10 to the minus third. That would be molarity. And I'm going to divide that all by 300 milliliters. Remember why 300 milliliters? Because my total volume here, my volume total is going to equal 300 milliliters. Okay, so I can calculate M2 for my silver ions. Okay, that's what I'm calculating here, my silver ions. So to do that, I would end up with a concentration of 8.67 times 10 to the minus 4 molar. Okay, so that's the concentration of the silver ions. Now I'm going to do the same thing for the sulfide. I'm just not going to show it here. I'm just going to plug that answer in here. Okay, so I'm going to calculate Ksp, and that would be my concentration, which is 8.67 times 10 to the minus 4, and I'm going to take that and square it. And then my sulfur, the sulfur ions, when I figure it out, will be 1.5 times 10 to the minus 5. Okay, you're going to calculate it the same way we did over here. Alright, so you plug all that in and you solve for Qsp. So my QSP comes out to be 1.13 times 10 to the minus 11. Okay, so what I want to do is I want to compare QSP to KSP. The KSP in this problem is to the 49th power. So clearly my QSP is very, very, very high compared to that low number for the KSP. Since QSP is greater than KSP, what does that say? Well, it's saying under the current conditions that I have, Q is greater. So therefore, remember, Q is the same thing as we said before. It's products over reactants. We just don't think about the reactants here. So really, QSP, if we think about it, is QSP is equal to the concentration of products. Same thing for KSP. KSP is essentially the amount of products you should have at equilibrium. Well, if I should have less ions at equilibrium, this reaction will shift in this direction and I will get a precipitate to form. So a precipitate forms in this reaction. Okay, so let's just kind of go back and recap what Q and K mean. QSP and KSP. Okay, so if my QSP equals KSP, then I'm at equilibrium. Oops. Then I am at equilibrium. Okay, so therefore if I'm at equilibrium, no precipitate forms. Okay, so that's what happens if my KSP and QSP are equal. If QSP is less than KSP, and I don't have enough products yet. If I don't have enough products, enough ions in solution, then it has to produce more ions and it will not form a solid. So no precipitate forms. The only time a precipitate forms is if QSP is greater than my KSP. Then I have a precipitate forming. Okay, it really takes a little bit of time to stop and think this through and understand. The idea is how many ions can I have in solution? That's what KSP is telling us, the degree to which I can have those ions present in solution. Okay, so take a look at that one a couple times if you have to. It might take a little bit to understand, and I'll start answering some questions in class too. Alright, so let's take a look at one that goes a little bit more beyond, okay? Alright, so here we go. Calculate the equilibrium concentrations of each ion in solution when I mix this and this together, okay? So what I'm doing here is I'm going to be mixing two solutions together and I'm going to be looking for a precipitate to form. Alright, now we're going to assume that the precipitate forms in this problem, and we're going to go ahead and also keep in mind that we're combining solutions together, right? We're combining this beaker with this beaker here, so our total volume at the end of this problem is going to be a total of 80 milliliters, or equal to 0.080 liters, okay? So keep in mind we're going to have a total volume. Now, the strategy that we're going to take with this problem, because I want to find out the concentration of ions in solution, what we're going to do is we're going to break this up into two parts. Part one is going to be let all of the solid form. Okay, what that means is I'm not worrying about solubility. So there's no ice table here. No ice table. No equilibrium. Okay, so there's no ice table and no equilibrium here. So what we're going to use is we're going to use a BCA table. Okay, so one of these reactants is going to go to 0. So I'm going to come in here and I'm going to let the solution form by taking these two beakers and pouring them together. And the beakers I'm talking about are this one and this one. I'll pour them together into this container. I got my solution here and a solution here. And what's going to happen is I'm going to form a solid. I'm going to make all of the solid form as I possibly can. That's step number one. Step number two is to then let equilibrium be achieved. Okay, so then I'm going to let the solution, or I'm sorry, let the solid dissolve. Okay, so if I let the solid dissolve, what that means is that I will have equilibrium. So here's where the equilibrium will come in. And since I have equilibrium, I'm going to do is use an ice table for this. Okay, so that's the second part. And the second part is that once I let this all form, then it will go into ions. Then it's going to start to dissolve. And that would be step number 2, that we form our ions in solution all around the outside. Okay, so let's do this mathematically. Okay, step 1. Alright, we're going to go ahead and take the calcium ions. Because we're not doing equilibrium, I'm just doing a stoichiometry problem. What I'm going to do is let these two ions come together and create calcium fluoride solid. This is going back in time to a BCA table. And what we're going to use here are moles. So I'm going to plug my moles into this equation. This is 0. And I'm not going to show you, you should know how to do this. I'm just going to use the, molarity of the volume times molarity. If you need to, go back and watch the videos on how how to get the number of moles from a solution. I'm multiplying the volume times the molarity. All right, to do that, after I do that, I get 3.0 times 10 to the minus 4 moles of calcium. Okay, so that would be moles of calcium. My fluoride is 1.2 times 10 to the minus third moles. Okay, this is going to decrease by x, decrease by 2x, and this is going to increase by x. So one of these two is going to run out. So I'm going to have to do a limiting reactant calculation, and I'm going to assume that because I need twice as many fluorides as I do calcium, I'm going to assume that the fluoride is going to well, actually, I'm going to kind of cheat here. I know that this goes to 0 because I already calculated it. So I'm going to start with looking at how many moles of fluoride ions. Okay, so a little recap of limiting reactants. So what I do is I take my 3.0 times 10 to the minus 4 moles, and I just do a stoichiometry calculation between moles of calcium and my moles of fluoride ions. So that would be a 2-to-1 ratio. So therefore I need to have 6.0 times 10 to the minus 4 moles of fluoride, which I clearly have enough of. So therefore this is my limiting reactant. Okay, so this is confirmed now that that is my limiting reactant. So therefore at the end of this I'm going to take this and I'm going to subtract out the 6.02. And when I do that I end up with 6.0 times 10 to the minus 4. And this is over here 6.0 times 10. Actually it'd be 3, but it doesn't matter because it's a solid anyway. We don't care about that. What we care about is this, and this is moles, don't forget. Okay? So now what we've done is we've converted this as far as we possibly can and force this reaction mathematically all the way to a solid. That's the idea here. We force it all the way to a solid. Now let's go to step 2. Now that we've formed all that solid, we're now going to let that solid shift back a little bit and start to dissolve and break down into ions. And this is where the equilibrium comes in. So this is where we get into the ice table. So we're going to have 2 fluoride ions, and we're going to start with ICE. And again, the solid is irrelevant. We're concerned about this. Calcium is going to be 0 because it starts out as 0. So whatever I have at the end here is what I'm going to plug in for my ice table initial here. Now, my fluoride ion is going to be 6.0 times 10 to the minus 4. But remember, I need molarities in ice tables. So this has to be in molarity. So make sure that you plug in molarity into the ice table. Okay, so I have to figure out the molarity of this. So I'm going to take that 6.0 times 10 to the minus 4 moles, and I divide this by my total volume. Remember what I said my total volume was 80 milliliters. So 0.080 liters will get me my fluoride ion, and that comes out to be equal to 7.5 times 10 to the minus third molar. Okay, so that would be my concentration of the fluoride. So 7.5 times 10 to the minus third molar, plus x plus 2x, x 7.5 times 10 to the minus third plus 2x. K is really small, so that's going to drop out. So then what I do is I just plug into my KSP and then I solve. What I'm looking for is x, because I already have my solubility of the fluoride. This is going to be the answer for the fluoride because it doesn't change much. You're not going to have much of a shift. So if I plug in KSP and I do just like I've been doing in all the other KSP problems we've been looking at, what I'm going to have is calcium times the fluoride squared, plug in the numbers, x 7.5 times 10 to the minus third, sorry about this, getting a little sloppy because I'm running out of space here, 10 to the minus third, and then what I would do is I would square that, set that all equal to my KSP, which is given here, 4.0 times 10 to the minus 11. Solve for x, because x is the calcium concentration. And that answer is going to come out to be 7.11 times 10 to the minus 7 molar. Very, very small amount of chloride ions, or calcium ions. Okay. If you want to figure out the concentration of the chloride and the sodium, it's pretty routine. There's no reaction. You're just going to use the M1V1 equation to figure that out. Okay, I'm just more concerned about this. So, hopefully you can kind of see all the nonsense here, but the general idea, shift the reaction to completion, meaning that we form as much solid as we possibly can. That's our first step, and it's a BCA table using moles. Then we take the results of that and plug it into ice, and then we allow the reaction to then go to equilibrium and shift back to ions. And this isn't what really happens. It doesn't happen in two steps like this. But mathematically, there's no way we can do this unless we kind of manipulate things a little bit. Okay? Alright, there is one more type of calculation, but I'll save that for class because I think we've got enough videos here for now. So that's pretty much it. So I'll see you guys in class.